Okay, so in this lesson we're going to talk about electric forces and electric fields. If you remember back to grade 11, we have talked about electric forces before, and before that we even talked about what does it even mean for something to be electrically charged. So if you'll recall, electric charges come in two varieties, positive and negative. And so a negative charge is the charge on an electron, for example, and a positive charge is the charge on a proton, for example. Most objects are neutrally charged. So in other words, they have the same number of positive charges as they have negative charges. But you can potentially charge something or give it a charge by, say, rubbing it with some kind of material, or you could actually induce a charge, but that's kind of beyond what we're talking about here. The SI unit of charge is the Coulomb, okay? And the Coulomb takes its name from Charles-Augustin de Coulomb, who was a French physicist who basically developed Coulomb's law, which we'll get to very shortly. So one of the experiments that we're going to be talking about a little bit later, Millikan's experiment, allowed him to deduce what is known as the elementary charge, which is the smallest amount of charge that you're actually able to have. So you can't just have any amount of charge that you possibly want. There is actually a lower limit, and that's what's known as the elementary charge, 1.602 times 10 to the negative 19 coulombs. And that's equal to the charge on one proton, okay? Because the number given, of course, is positive, and a proton has positive charge. If the number were negative, then that would be the charge on an electron. But in this case, the elementary charge is given as a positive number, so that's the charge on one proton. Okay, so now we get into electric force. So this is basically a force that is exerted or felt by something which has an electric charge. So if you have two charged objects, then they will experience a force of attraction or repulsion depending on what their charges are. And so what Coulomb discovered is that the force is proportional to the product of their charges and inversely proportional to the square of the distance between them. So this is Coulomb's law, right? And so you can see in the numerator here we have the product of the two charges, Q1 and Q2, the inverse square law. So in other words, we're dividing by the square of the distance between the two charges, and then you have this K out front, sometimes called Coulomb's constant, which is just a proportionality factor. So that numerically has a value of approximately 9.0 times 10 to the 9 Newton meter squared per Coulomb squared. Okay, again, the units here are just to make sure that in the equation, once you put in all the other quantities, you get newtons as your final units, because we are, after all, calculating the electric force. So, of course, the other thing that's built into this that maybe isn't obvious is that the law of electric charges tells you that if you have two like charges, like let's say two protons, then those will repel each other, right? Likes repel. But if you have opposite charges, let's say a proton and an electron, then those attract, right? Opposites attract. So that's basically the law of electric charges, and the way it's written out here with the little r hat vector, just make sure that if you have an attractive force, meaning that the two charges are opposite in sign, then it would actually be an inward force, which is how that has to go. So let's look at a problem. Determine the magnitude of the electric force between an object with a charge of positive 1.0 microcoulomb and another with a charge of negative 4.0 microcoulomb separated by a distance of 2 meters. So one of the things when working with charged objects is to realize that having an entire coulomb of charge is really unusual. Typically in atmosphere, an object will get somewhere on the neighborhood of a microcoulomb of charge, let's say by friction or some other process. And once it gets up to about a microcoulomb, then pretty much anything nearby that it can discharge into, it will. So, so there are definite limits on how much charge something can hold, how much data charge something can hold. You know, and the only way to kind of get around that, you know, to hold more charge onto something would be to put it in, say, a vacuum. But that's kind of getting ahead of ourselves. So we just want to determine the magnitude here, and obviously it's pretty straightforward. We're going to use this Coulomb's law and plug in our values. Now, before we do that, we have these microcoulombs, and again, micro is the SI prefix for 10 to the negative 6. So once I put the numbers in here, you'll see that for Q1 and Q2, I have that 10 to the negative 6 number in there. All right. Anyway, you work this through, and in this case, because it only says the magnitude, I don't actually technically need to worry about the negative sign, but whatever, I've put it in for now. And so I have this number. Okay. Now again, the magnitude technically would ignore the negative, but I've left the negative in just to remind myself that because these two charges are opposite in sign, one's positive, the other's negative, that this would be an attractive force. Okay, so I've just left that in there to remind myself, although technically speaking, I have that information just in the problem itself would tell me that. Okay, so now we're going to go on to electric fields. So an electric field is very similar in some respects to a gravitational field that we talked about last time. Essentially, we're going to start with the idea of a point charge, so some charged object that is very, very small in space, although I guess it could be larger, but nevertheless. And then we're going to surround it by a grid. Okay, so we have our point charge, and there's going to be a grid around it. And then what we're going to do is we're going to have vectors indicating what direction a positive test charge would go, as well as how much force would that positive test charge experience. Once we have all these vectors, then we can actually connect them up to create the electric field lines. So this is basically where we just draw through the vectors to create continuous field lines that never cross. And essentially, once you have the field lines drawn, then you can tell how strong the field is by how dense the field lines are. The electric field, mathematically, is given by this equation. Now, if you go back and you look at the equation for the gravitational field, you'll see that it has a very similar character, except that in this case, instead of capital G, I have lowercase k. And instead of big M, I have lowercase q. But I still have that 1 over r squared behavior. Again, this electric field is a vector. Okay, it is a vector. So the idea here is that the vector symbol is such that, or the vector quality is such that wherever I am in my field, there is a vector there. So it's not just, so again, the idea of a field by itself is a little mysterious, but all you really need to think about it as a whole bunch of little vectors that together tell me what is going on. The units of this, if you work it through, are newtons per coulomb. That's the most common way of writing it. However, sometimes you also write the units as volts per meter, which turns out are equivalent units. Volt per meter make a little bit more sense when we talk about the geometry of a parallel plate electrodes, but we'll talk about that later. So for now, we're just going to worry about newtons per coulomb. Okay, so this is basically what I'm talking about here. Okay, so the red dot in the middle is my point charge, and you can see that all around it there's a grid, number 1, and then at various points in the grid we basically draw vectors indicating where would a positive test charge go. Where, if I put a positive charge nearby my red positive charge in the middle, what kind of force would my charge experience? And because two positives would repel each other, if I were to put a positive test charge, below my positive charge, then it would get repelled away. It would go down. So that's why those vectors are outward, radially outward. And to draw the field lines, all you need to do really is just imagine connecting up the vectors as a line. If my inner charge is negative, then it's the same idea except in the opposite direction. All the vectors point inward. Okay, all the vectors point inward, radially inward, so that that's how that one would go. But it's really the same kind of idea. Okay, so again, whenever you're drawing your lines, one of your field lines, you're always trying to think which way would a positive test charge, what kind of force would a positive test charge experience? Would it be an attractive force, or would it be a repulsive force? Okay, so here's another problem. Let's say that I have two charged spheres, and the first one has a charge of 3.2 times 10 to the negative 9 coulombs, and the other one has a charge of negative 6.4 times 10 to the negative 9 coulombs. And the two charges are separated by 42 centimeters. What I want to do is I want to calculate the net electric field at a point P, 15 centimeters from the positive charge. So this is the setup here. Okay, so red represents positive charge and blue represents negative charge, and P is the point, basically the one point in space where I'm actually going to do the calculation, where I'm going to calculate the net electric field. Now before I pull out the equation, I just want to have a think about this. If I were to put a positive charge where P is, which way would that positive charge want to go? Well, okay, let's think about this. If the blue charge weren't there, if the negative charge weren't there at all, then the red charge would tell the positive charge at P, hey, get away from me, right? Because they would both be positively charged, and so there would be a repulsive force. So in that case, P would experience a force to the right. Okay. However, if the red charge weren't there, and the blue charge were the only charge, in that case, the positive charge at P would want to also move to the right because it's attracted to the negative charge. So when we take these two things together, they're both going to create forces that move the test charge at point P to the right. Okay, so the positive charge, the red charge, pushes it to the right, and the blue charge, the negative charge, pulls it to the right. So both of these are going to add together and give me an electric field pointing right. So that's why the last line of my text, it says, let right be the positive direction. It's already kind of setting up the problem so that I've taken care of the direction of my vectors, right in this case being the positive direction. So if I go to my math, then I basically have this equation. So again, in this case, I have to add together the electric fields from the two different charges. And again, they are added because they're both pointing to the right. So really, it doesn't matter what I put in the values from my Q at this point. I've already taken care of the signs. So in this case, it's just a matter of plugging in the numbers and chugging it through, and I get a total electric field of 2.1 times 10 to the 3 newtons per coulomb pointing to the right. Okay. Now again, this I was able to, if I just go back a second, there we go. Again, everything is adding together because both of the electric fields, the electric field from the red charge and the electric field from the blue charge, are both pointing to the right. Now, what if they weren't? What if instead I had a red? What if both of the charges, Q1 and Q2, were positive? Well, in that case, Q1's electric field would point to the right, but Q2's electric field would point to the left. So in that case, I'd have to choose one direction to be positive, and then in my equation, I'd have to subtract the two electric fields, depending on which way I chose to be the positive direction. In this case, I didn't have to, so that's nice. Okay, so I mentioned earlier something called a parallel plate geometry. So parallel plate geometries are very, very common in physics and engineering for a couple of different reasons. But for now, the idea here is that we just imagine two parallel metal plates. Okay, so like almost like two slices of bread, except they're made of metal, and they're going to be some distance apart. Okay, so the idea is what you generally do is on one plate you have a positive charge, and on the other you have a negative charge. Pretty simple. So what's going to happen is that because you have all these different charges, the electric field between them is going to be constant. So in the space between the two plates, the electric field is constant, right? It's pointing towards, well, I mean, it would be pointing from the positive plate towards the negative plate, in much the same reason that we did in the previous example. So that's basically how that works. The field lines always point from the positive plate to the negative plate because, after all, that's what a positive charge would want to do. And outside the plates, this is the cool part. Outside the plates, the electric field is theoretically zero, although that's not exactly true. There is normally something called edge effects, which is basically a slight bulge in the electric field, but that's not something that we normally consider. Okay, so basically, in an idealized situation, there's a constant electric field between the parallel plates and no electric field outside of the parallel plates. Funny thing about this is that the electric field actually only depends on the charge of the plates. It doesn't actually care about the plate separation. Now again, in reality, that's not really true because the farther apart the plates are, the more of these bulging or edge effects you get. But at least for our purposes, you sometimes hear about infinite plates, so that you actually don't even have to worry about edge effects. That just means that the size of the plates is large with respect to the separation, but that's fine. Anyway, so the idea here is that the actual plate separation, how far apart the plates are, doesn't actually make a difference. All that matters is how much charge is on the plates. Okay, so with that out of the way, I just want to set you up and get you working on these homework questions. They're pretty similar to what I covered in the lesson earlier, so just give them a try and see if you can work the magic and come back here for another lesson. Thanks.